white matter, gray matter, you do need to know white matter and gray matter. We'll talk about it again in chapter 12, okay? White matter is regions of the brain and spinal cord with dense collections of myelinated fibers. Gray matter is neuron cell bodies. We'll talk about it again in chapter 12. So understanding white matter and gray matter in chapter 11 helps you know what white matter and gray matter does in chapter 12, okay? So that's something to key on. We already talked about glial cells and neuroglia, all right? And that shows that. Now, when you talk about your types of neurons, there's three types. There's multipolar, bipolar, and unipolar. The picture that we saw, if we back up here, that's a beautiful picture of a neuron. If I didn't say it, that's a good picture, really, really good picture. You might see again, okay? But in reality, neurons don't look like that, all right? There's multipolar neurons, which have 3 or more processes. Bipolar neurons that have 2 processes. Unipolar that have 1 process. And to show you what that looks like, here, these are multipolar neurons. So that one that you saw, which I said was a real good picture, in reality, it probably looks, it's weird lake shape like this, okay? It has 3 or more processes, which means a dendrite here, and an axon sticking out. Usually has more than that, all right? It can have hundreds of processes sticking out. But if it has more than 3, it's multipolar. If it has 2 processes, axon going this way, 1 dendrite going that way. Same thing over here. 1 axon, 1 dendrite. Just because the dendrite branches doesn't make it more than 1. It has to branch from the body, okay? So these are called bipolar. And then unipolar neurons are like this. So I want you guys to understand that in reality, the nerves in your body don't look like that beautiful picture that we see. That beautiful picture helps us understand what a neuron does, okay? All right. Functional classifications of neurons. There's sensory neurons and motor neurons. This should just make sense. Sensory neurons make, I'm sorry, I thought it was fine. But sensory neurons, your senses. Sight is a sensory neuron. Smell, sensory neuron. Touch, sensory neuron. Your senses are sensory neurons, all right? Motor neurons are neurons that are sending a signal to the body to tell you what to do in response to what you have seen, felt, tasted, or whatever, okay? Or another way to describe it, sensory neurons are afferent, AFF. Remember afferent and efferent?
Afferent goes in, efferent comes out.
Exactly. Motor neurons are efferent. Okay. And then there's interneurons. These are association neurons. These are mostly found in the central nervous system. These are most of the body's neurons. These are the ones that you find in the brain and the spinal cord. So really, to make it overly simplified, if something pricks my finger and my pinky, there's a neuron in my pinky, which is a sensory neuron that sends the pain of the prick from my pinky to my central nervous system. My central nervous system is going to tell me to move my pinky, okay? But the nerve that comes from my central nervous system to my pinky is a motor neuron. In between the sensory neuron and the motor neuron is a interneuron, which is in between. All right, that just breaks down multipolar, bipolar. We can skip that. And greater potential, action potentials. We got to talk about this before we start skipping some stuff. On the bus. All right, greater potentials, action potentials. All right, greater potentials and action potentials, they're both signals that move in a nerve. There's a difference though. Greater potentials decrease over time and distance. Action potentials do not decrease over time and distance. Another way to say that. Greater potential is like rocks in a pond. You throw rocks in a pond, you know how it makes the ripples? But the further and further you get away from where the rock went into the pond, the smaller, the more gentle the ripples become. That's a greater potential. And action potential is whatever you throw the rock in the pond is different. This really doesn't happen. But if you throw a rock in the pond, the waves from where the rock went into the pond are big, and the waves at the edge of the pond are the same size and the same force as where the rock went into the pond. So an action potential does not decrease over time and distance. The same strength that action potential is when it begins, it's the same strength when it reaches the axon hillock, okay? So this is the difference between graded potentials and action potentials. Graded potentials decrease over time and distance. Action potentials do not decrease over time and distance. Is that making sense? You got what you need to know about graded potential and action potential, okay? Now, I'm gonna back up some slides to help us understand so we can skip a bunch of slides, okay? Backing up to here. All right, so here's your beautiful picture, right? When you receive a signal, a graded potential comes in from the dendrite. It starts as a graded potential, and the graded potential goes from the dendrite to the axon hillock. This is a graded potential. So it's decreasing over time and distance. You remember it's talking about threshold? So if the graded potential from here is enough to create a threshold stimulus here, then we automatically get an action potential which goes all the way down the neuron, the axon, okay? And then whatever strength the action potential is here, it's the same strength when it reaches here, okay? It's never gonna change. This is how graded potentials and action potentials work. There's some signals that might create a graded potential here that doesn't create a big enough signal here to make it go to threshold. Then you don't get an action potential, no action potential, no neurotransmitter release, no neurotransmitter release, then you don't realize what's going on. For instance, there's an insect or something crawling on your skin, you don't feel it. It's creating a graded potential, but it's a small graded potential. And that small graded potential is not creating an action potential here. So there's no neurotransmitter release. The brain doesn't realize that something's crawling on your skin. Does that make sense? Okay. We can skip a bunch of slides now. Here. All right, depolarization, hyperpolarization. I'm gonna skip ahead to show you guys depolarization, hyperpolarization, all that, because I can skip all this stuff here. Get to the picture. Where's the picture? Here. All right. I'm gonna back up and just make sure there's nothing else important that I missed, but you get this, all right. So, in a neuron, -70 is the action potential or the resting potential. Depolarization, just like in the muscle cell, is coming up, becoming less negative. Repolarization is coming back down, all right, becoming more negative. Then, unique for the neuron, it has this little place where it goes, dips under a little bit. That's called hyperpolarization, okay? And then it returns to normal. Then you go through the normal process as usual, right? So you have basically three different phases. You have your relative refractory period here, absolute refractory period here, and this is the period where easily activated where depolarization occurs, okay? When it's at -70. Same thing as in the muscle cells. Sodium's coming out here, potassium's coming out here, sodium channels are closed there. So same thing as in the muscle.
Neurons communicate over long distances by generating and sending electrical signals called action potentials. Most action potentials originate in the axon's initial segment, a region also called the trigger zone. During an action potential, voltage-gated sodium and potassium channels open and close, thus altering the membrane's permeability to sodium and potassium ions. As these ions diffuse through the channels, the membrane potential changes. It depolarizes from the resting state of -70 millivolts to a peak value of +30 millivolts, and then quickly repolarizes back to -70 millivolts after a brief period of hyperpolarization. In this topic, we explore, step by step, the events that occur as an action potential is generated in the axon's initial segment.
All right, now, that axon initial segment they mentioned, that's come in the next slides that we're skipping. That's also what I call the axon hillock. They call it the trigger zone. All right, same thing, okay, that's what you're looking at. And then we'll skip all that. Well, I mentioned this threshold. Hopefully you guys understand threshold, but in the nervous system, threshold is whenever the membrane is depolarized by 15 excuse me, to 20 millivolts, all right? So, resting potential, anybody remember what that was? -70. So minus 55 or minus 50 is an automatic action potential. So if the graded potential creates a signal that pushes it to minus 55 or minus 50, you're going to get an action potential. If it pushes it from minus 70 to minus 60, you don't know that bug is crawling on you. You don't know that something is touching you. You can't smell whatever, it's not enough, okay? So this is, again, what threshold is. And as I mentioned with action potentials, they are an all or none. They don't decrease over time and distance. Whatever strength it is when it starts, it's the same strength when it is. All right. This is another quick video on action potential, talking about how it propagates and moves.
Action potentials propagate in a continuous fashion in unmyelinated axons. Once an action potential is generated in the initial segment of the axon, it propagates the entire length of the axon. Recall that a threshold stimulus causes voltage-gated sodium channels to open. The influx of sodium ions generates an action potential. It also establishes a depolarizing current that flows to the next segment and brings it to threshold. Voltage-gated sodium channels open, regenerating the action potential in this segment of the axon. Current flows from this segment and depolarizes the next segment to threshold, thus regenerating the action potential yet again. In this way, regeneration continues in one direction all the way down to the axon terminals. The basis for unidirectional propagation is revealed when we take a closer look. By the end of the depolarization phase of the action potential, all voltage-gated sodium channels inactivate and voltage-gated potassium channels open. These two events render this segment of the axon temporarily insensitive or refractory to another depolarizing stimulus. However, voltage-gated sodium channels in the downstream segment are closed and receptive to a depolarizing stimulus. Thus, propagation occurs sequentially down the axon to the axon terminals. In myelinated axons, action potential propagation is a bit different. Here they propagate in a saltatory or leaping fashion. The myelin sheath consists of multiple layers of tightly wrapped glial cell membrane. But this sheath is not a continuous one. Exposed areas of axonal membrane, known as nodes of Ranvier, occur at discrete intervals. Voltage-gated sodium channels are abundant in the nodes, but largely absent between nodes. So, action potentials are regenerated at each node, not in areas covered by the myelin sheath. However, the myelin sheath does provide the insulation necessary for the rapid spread of depolarizing current. And the sooner the nodes reach threshold, the faster action potentials propagate along the axon. Saltatory conduction is extremely fast. Velocities often exceed 100 meters per second. In contrast, continuous conduction is fairly slow. Velocities rarely exceed 2 meters per second. Nevertheless, both continuous and saltatory conduction propagate action potentials over varying distances because action potentials regenerate along the way. Summary: propagation of an action potential. Once generated, the action potential propagates the entire length of the axon without decrement.
All right, so essentially what that was talking about was myelinated axons and unmyelinated axons. Myelinated axons, that word they use saltatory. Saltatory won't show up on your test, but that's faster conduction with the myelinated axon, and it's a slower conduction, what they call continuous, with the non-myelinated axon. But the membrane has to change from 30 to 70, no, not 30, from minus 70 to 30, flip it, flop it, but from minus 70 to 30 each time. When you have the myelin, what happens is It only changes at each node, each of those spaces, and so it's faster conduction. All right. Coding for stimulus intensity, we will talk about this. All action potentials are alike and are independent of stimulus intensity. The central nervous system tells the difference between a weak stimulus and a strong stimulus by the frequency of the impulses. So in other words, all action potentials are alike. The action potential of sense of smell versus the action potential of the touch and taste, they're all the same, all right? It's all the same thing happening. The way that it works differently in terms of is it a strong smell or is it a gentle touch is the frequency, okay, of the impulses. Your brain counts the space between the action potentials. The more space between the action potentials, the weaker the signal. The less space, the stronger the signal. For instance, here, you see the space between these signals, you got a weak stimulus, enough but weak. Space here, same amount of space, but you got more signals, a much stronger signal. So this is how our brain tells the difference between weak and strong signals. Refractory period is the time which a neuron cannot, trigger another action potential. And then there's absolute and relative refractory period. We're relative on the next slide. Here, relative. Here's the difference between absolute. Absolute refractory period, there is no way at all that you'll create another action potential. Relative refractory period is it's much harder to create another action potential, okay? And that's essentially what you need to know there, okay? It just says threshold is elevated. So rather than 15 to 20, you got like a 40, 50 threshold. Here's this picture again we saw. And this again is the classic action potential for a neuron. What you have is resting potential is minus 70, depolarization, sodium channels are open, repolarization, sodium channels are closed. You got your hyperpolarization, returns to normal, and you have your absolute refractory period. You cannot create an action potential here. You have your relative refractory period where you can create an action potential, but the threshold is much more elevated in the relative refractory period than it is in a resting neuron. And on the bus. Easy peasy, lemon squeezy. All right. Propagation, or in other words, how fast an action potential moves, has to do with the axon diameter and the degree of myelination. The greater the diameter, usually the faster the signal. The more myelinated it is, usually the faster the signal. Continuous and saltatory, what you saw in the video or what you heard in the video. Continuous is non-myelinated axons. Saltatory is myelinated axons. And that just again explains continuous and saltatory. And this shows in an axon, well not an axon, this is a dendrite. It's a graded potential, because notice it decreases over time and distance. That's graded potential. Then you have continuous. So what happens is action potential starts here, it regenerates itself here, and it keeps regenerating itself, so it's the same force when it gets to the end. That's a non-myelinated axon. In a myelinated axon, here, notice it's going from one node to the next node to the next node. It spreads a lot faster because you lose less ions when it's myelinated. When it's not myelinated, you lose some ions out of the plasma membrane, or the neural limb. On the bus. All right.
So myelinated is faster?
Myelinated axons, yes, sir, significantly faster. And we'll give some data or some more facts on that at the end later. Multiple sclerosis is an autoimmune disease that affects primarily young adults, more women than men. Here, myelin sheath is attacked by the immune system. It destroys the myelin, the white blood cells do. They end up creating scar tissue called scleroses. And then when you have this scar tissue, there's no channels to propagate and send the action potential. So nerves don't work like they're supposed to, and muscles don't work like they're supposed to. Now, with multiple sclerosis, what happens is there's visual disturbances, weakness, loss of muscular control, speech disturbances, incontinence. Treatments, there are drugs that reduce the immune system to stop the immune system from destroying the nervous system so much. You can't prevent multiple sclerosis, but you can have some treatments. For instance, high blood levels of vitamin D, play a role in reducing the development and decreasing the risk. All right. Now there's three types of fibers in terms of nerves. There's group A, group B, and group C. Here's the easy way to remember group A, group B, group C, or what really it's easy, what you gotta know. Group A is the fastest, all right, 300 miles per hour, all right. Group, that's pretty fast in your body. Group B is about 30 miles per hour, still pretty fast. Group C is about 2 miles per hour, real slow, all right. Group C are unmyelinated. B are lightly myelinated. A, of course, are heavily myelinated. And those are the three groups that these fibers fall into. But all you need to know is A is the fastest, C is the slowest, B is somewhere in between. All right, on the bus. All right, the synapse. I'm not going to talk a whole lot about synapse. You already understand the synapse. Pre and postsynaptic neuron. I'm not really going to talk about that, but I'll give you guys this. It's simple. There's a presynaptic neuron and a postsynaptic neuron. The presynaptic neuron is the neuron that sends a signal. The postsynaptic neuron is the neuron that receives the signal. Hopefully that's pretty simple. Okay. All right. This gives some examples of pre and postsynaptics. Let me skip all that. Picture there. Neurotransmitters. We will talk about neurotransmitters. Yay, neurotransmitters, right? All right, here now, for neurotransmitters, there's about 6 or 7 different groups of neurotransmitters. You should know all the different groups of neurotransmitters, okay? Here's why. I often have some questions on the test that say which of the following is not a neurotransmitter. And I'm gonna list a few of these groups, and I'm gonna throw something else in there that sounds like a neurotransmitter, but it's not a neurotransmitter. Okay, so let's learn these groups. The first group is super simple, you know it, acetylcholine. That's the most well-studied, most well-known neurotransmitter. Normally it's exciting things, all right? So one group is acetylcholine. Simple, you know that. Next group is biogenic amines. That's a weird word, all right? But biogenic amines, all right? Dopamines, endolamines, things like that, all right? All you gotta know is biogenic amines.
We just have to know the names of these groups?
Just the names.
Perfect.
So here's my question. Please identify the following, which is not a neurotransmitter. A, acetylcholine. B, biogenic amine. C, polysaccharides. And you choose polysaccharides because I said not. Make sense? All right, but I'm gonna put a weird word in there. Next group, amino acids. I don't want you to know about glutamate, aspartate, glycine, GABA, any of that stuff. But here's the question again. Please identify the following, which is not a neurotransmitter. A, acetylcholine. B, biogenic amine. C, amino acids. Or D, I might say something like retinoblastoma protein. And you would choose retinoblastoma protein. Because I'm just gonna put a weird something in there, which is gonna make you go, what is that? Don't worry about what it is. All right, just know the ones that, the groups that are neurotransmitters, that's it. Here's the next group, peptides. I don't need to keep repeating the question, do I? All right, so peptides is the next group. So now you got multiple, now I got an A, B, C, and a D. And so you may not get all of these, but you'll get some of these, but you need to know which ones are. So peptides, purines. All right. So I can give you that list and not include, all right, acetylcholine. Which of the following is not a neurotransmitter? Peptides, amino acids, biogenic amines, or whatever, glucose. You got to figure out which one is it. Then there's gases and lipids also, which is another group. And we got 2 more groups. How many groups is that? 5 already?
6.
We got 6 already? Ooh, I lied. I said there were 5 or 6. There must be 8. Endocannabinoids is another group. That's the ones related to marijuana and THC. All right. endocannabinoids. And then the last group, oh, no, that's the last group, okay. So we got 8 groups, 7 groups. All right, I missed that. Questions there? All right, we are essentially done with chapter 12. We're not gonna talk about any of that. Well, this last thing I will talk about. All right. Remember at the beginning of the chapter when we saw a glass of water, you decided you wanted to drink a glass of water, and you reached out and drank a glass of water. There were 3 steps. All right, in the very beginning of chapter 11, all right, there's really 5 parts of that process, all right, because there's the receptor, the eye, that sees the glass of water. Then the signal has to travel on a sensory neuron, afferent, into this little brown region, which is the central nervous system. Here, there's the interneuron, which is the integration, that's step 3. Then a motor neuron goes to the muscle to tell the muscles to reach out, grab a glass of water, drink a glass of water. And so this is the process through which all, this is called a reflex arc. This is how the nervous system works. You receive something as a sensory signal and you respond, okay? If you, again, something pricks your finger, the reflex arc that it goes through is step 1, 2, 3, 4, 5 before you move your finger, all right? If something, whatever, is crawling on your skin, reflex arc is 1, 2, 3, 4, 5 before you move your hand or swat whatever bug is on your skin, whatever it is, okay? So it travels through this reflex arc. And in the next set of chapters, we talk about receptors, sensory neurons, the integration center, motor. And this is what the next chapters deal with, just more detail, okay? On the bus, I'm using the abbreviated PowerPoint, which is for you guys on campus. You should be able to see that. All right, there's an abbreviated 12 through 14 where I'm still gonna skip stuff, but I took out even more stuff. All right, and I advise you guys to use that more for your study than the traditional ones. If time was permitting, I would go through the traditional chapter 12 and talk about a lot of other stuff. We just don't have that time. All right, ready for chapter 12? Any questions on 11? All right, now, remember as I said in the beginning, I spend more time on 11 than I do on the other chapters, so I'm gonna skip over a lot of stuff, okay? All right, chapter 12, brain regions, hemispheres, diencephalon, brainstem, cerebellum. You've already seen these, all right, in the sheet brain. Here's the picture to help us understand. The cerebrum that you saw, all right, that's the cerebral hemispheres, all right. The diencephalon, remember the thalamus? That's the diencephalon. The diencephalon is what we call it in humans, okay? And then there also is a thalamus in the brain also. But then the green is the brainstem. Midbrain, pons, medulla, and of course, not part of the brainstem, but when the brainstem transitions from brainstem, it becomes the spinal cord down here, all right? And the cerebellum is there, right? So we've already seen that. You should be able to identify those on the human brain. Spinal cord, all right. We wanted to talk about that there. Gray, white matter. All right, gray matter, white matter. Anybody remember that? We just talked about it? Gray matter is cell bodies, white matter is myelinated axons, all right? So with that, there's a pattern of gray and white matter in different parts of the brain. Here, this part, the dark is the gray, the lighter color is the white. Dark gray, lighter white. So for those going into maybe radiology, taking images and all that, they tell you to take an image of a certain part of the central nervous system and you come back with the wrong image, they know by just looking at the gray matter often. Yeah, you got the spinal cord, but it's the wrong part of the spinal cord because they can look at the gray matter and tell. All right, real simple. So gray matter, white matter are in certain patterns, okay, throughout the body. The brain has ventricles in it, fluid-filled chambers, all right? They're all connected, so there's fluid flowing in the brain, but the brain is also floating, excuse me, in a fluid lined by ependymal cells. If you remember the beginning of chapter 11, we talked about glial cells. Ependymal cells were one type of glial cell in the central nervous system. These fluid-filled chambers have CSF, or cerebrospinal fluid, in it. All right, there's 4 ventricles in the human brain, 2 C-shaped ventricles in the cerebral hemispheres, a 3rd ventricle in the diencephalon near the thalamus, which we call the lateral ventricle in the sheep, and then the 4th ventricle in the hindbrain. Here's a picture that shows these 4 ventricles. All right, you don't have to know the ventricles, just know there's fluid-filled chambers, and know ventricles are fluid-filled chambers. I won't ask you to identify or name them, okay? But 1, 2, 3, and 4, and from a side view, 1, 2, 3, and 4 are these ventricles. All right. On the bus.
So we don't need to know 1, 2, 3, or 4,
Just know there's fluid-filled chambers. All right. Surface markings, we already talked about this in the sheep brain. Frontal, parietal, temporal lobe, occipital lobes. All right. The insula is new.
Where is that one at?
We'll talk about it in just a minute. We'll get there. It's coming up. All right. And then there's gyri, which are wrinkles, okay? And fissures, which are a deep groove. And foci, I'll mention to you, but foci won't show up on the test. All right. Then I'm going to skip all that there to the picture. Here. So when you look here, the wrinkles you see in the brain, these are the gyri. All right. You see gray and white matter here. The dark is the gray, the light is the white. So the edges of the brain are gray matter. You see here they're divided into frontal, parietal, occipital lobes. The lobes are divided by a sulcus. A sulcus is deeper than a gyri, but not as deep as a fissure. But again, sulcus is not going to be on the test, all right? But I want you guys to understand when if you hear the word sulcus, what it is. The gyri is a small little wrinkle. Sulcus is deeper than that, so there's a kind of deep groove between these 2 lobes. All right, but it's not as deep as the longitudinal fissure, okay? Here, the insular lobe, if you pull back these lobes where the thalamus is, or the diencephalon, this is the insular lobe there of the brain. So the brain has more than just a frontal, parietal, temporal, occipital lobe. If you go deep on top of the brainstem, all right, that is also the insula, or that is the insula.
So if they were going to do surgery, like something happened in that part of the brain, they would have to open that. Anything ever happened?
Surgery in the insula? Yeah, I'm imagining that's possible. Yeah, when you even talk about that, I don't think they would really open it up because brain tissue is so fragile. Our brain tissue really is like an egg, so like the inside of an egg. So if they start pulling stuff apart, it is never going back where it's supposed to be. But I could see them using, kind of like the robotic surgery where small, laparoscopic type surgery going in, and you would damage some tissue to fix the other tissue in that process. Yeah. But here again, another picture of the brain. You can see the gyri, the wrinkles here. You see the longitudinal fissure here. The brain actually has blood vessels, arteries and veins on it. This side, the arteries and veins are removed for a more clear image of the brain tissue. Here, another picture of the brain here from the side view. This is the transverse cerebral fissure. You don't have to know that. But when you're looking at your sheep brain, if you notice that the cerebellum is kind of falling off, because this transverse cerebral fissure is a deep groove there. And of course, the brainstem here, your brainstem is your pons, your medulla, and the midbrain. On the bus. We've already seen the gray matter, which is that thin layer on the cortex, the outer part of the brain, but this is just explaining that. 2 to 4 millimeters, 40% of the mass of the brain. And this is where your conscious mind is: awareness, sensory perception, voluntary motor initiatives, communication, memory, storage, and understanding. In other words, all the parts that your brain that make you in terms of how you function, and you in terms of memory, and you in terms of personality. All of that is in a thin 2 to 4 millimeters on the edge of the brain, the cortex. Okay. Deeper in the brain, it's mostly myelinated fibers sending signals to different places. All right. Now each hemisphere connects to the contralateral side of the body. We won't spend a lot of time with that. And there's lateralization of function in the hemispheres Three types of areas, you should know these: motor, sensory, and association areas. Let's talk about these. A motor area is responsible for controlling voluntary movement. All right, if you're moving your arms or whatever, I'm moving my legs because I'm walking back and forth, that's a motor area of the brain. A sensory area, you're common when you think about our senses. Those are usually afferent. Then association areas are areas that integrate diverse information. Now, there'll be some more slides on this, but hopefully I can skip them. Diverse information is when you take two or more pieces of information to figure something out. We do it all the time. You can touch something and say that this is cold and smooth. That's two pieces of information. I'm having to use a association area to make sense of that, because smooth is relative to other things that I've touched. Cold is also relative to other things that I touch. So I'm making an association based upon one thing, all right? Or you can say something is warm and fuzzy, or you know, these are associations. So they're areas of the brain that take different senses and combine them, okay? Those are association areas. Some of the motor areas here, you don't really have to know those. Broca's area, I encourage you guys to be familiar with, because if you take standardized tests, it'll pop up here. I think it's on your post-test, Broca's area. But Broca's area is often in standardized tests like your GREs, ACTs, and other types of tests like that. Broca's area, you know those tests where they give you, like, you gotta read this passage, you know, and then they ask you questions on it, and you're like, I don't even know what they were talking about. And it's really not testing whether or not you understand Broca's area. It's really testing your reading comprehension. All right. But Broca's area, one of those things that they like to put in those ACT, GRE type tests, they'll pull in Broca's area and put something in on that. So it's good to know what Broca's area is. This is what Broca's area is. It is an area of the brain that is involved for motor muscle movement for speech. So my Broca's area right now, if somebody was measuring my brain, it should be lighting up, because I'm doing all the talking, all right? For someone who's not doing much talking, Broca's area is not that active, but it's the muscles involved in speech is what Broca's area controls, okay? In Broca's area, to see where it is, it's this little dashed line here. This is a wonderful diagram that I used to scare students to say it's on your test. It's not, it never is. But this maps out all the different areas of the brain. Where is seeing over here, and where is taste, and so on and so on and so on. The gray matter of the brain has something called, and I don't think this is on your test, but this is something you should still know, called homunculi, all right? For movement, they're called motor homunculi. They're upside down caricatures representing the motor innervation of body regions. What does that mean? Or what does it look like? This here. So in the brain, they map out the brain by saying there's a place in the brain that controls the jaw, the eye, the brow, the thumb, and so on and so on. This is where the nerves to move the thumb get their signal from. All right. And they have these upside down, what are called homunculi, to map out these regions of the brain and where things are. In the same way that you have motor homunculi, you have sensory homunculi. And I'm gonna skip to, well, no, it's too far. But anyway, this is your motor homunculi. Premotor cortex, we won't talk about. Broca's area, I mentioned to you already. A motor speech area that directs the muscles of the tongue.
But it's not on our test?
Broca's area? I mentioned, I know it's on the post-test. I said post-test, yes. But let's just talk about all of this. Premotor cortex, you guys, just so you understand. Premotor, pre means before, right? Motor means movement. So premotor is there's an area of the brain that's involved in planning the movement before you have the movement. So you're thinking about how to do the movement before you do the movement. That's the premotor cortex, all right, essentially. Very learned repetitious or patterned motor skills. Driving, all right, comes from our premotor cortex. I know it's noisy, but I'm sorry. but driving from the premotor cortex, because there's some things you do driving that are just instinctive, right? You don't even have to think about it. You know, you see lights of a car in front of you, you automatically start braking. This is premotor cortex type stuff, okay? Broca's area, we said, involves what? Speech. Frontal eye field, that's simple. It's going to control what? Your eye movement. All right. Sensory areas. Now, I was going to talk about these because you need to understand sensory areas. These are words that hopefully you have a bit of an understanding on. All right. But these are like kind of vocabulary. All right. They help you in the coming chapters. There is the primary somatosensory cortex and the somatosensory association cortex, okay? Primary soma means body, okay? So soma means body. So if something touches your forearm, your primary somatosensory cortex tells you it's touching my forearm. The somatosensory association cortex says there's something sharp touching my forearm. Sharp is an association. Or there's something cold touching my forearm. Is it making sense there? So that's the association of what's going on. Visual areas make sense because these are that control what? Vision, all right, sight. Auditory areas are involved.
Hearing.
Good. Weird word, you should know this by now. Olfactory. All right, involves what sense?
Smell.
Smell. Gustatory. Taste. All right, you should know this, all right? This is what you also got to know. Visceral sensory area. Visceral, what's an example of a visceral organ? Yeah, stomach, if your stomach's upset, that's visceral. Full bladder, that's visceral. Internal pain, intestines, you know, some liver, kidney, all this. These are all visceral, so internal organs, all right? And then there's a vestibular cortex. Anybody know vestibular? Vestibular and auditory actually go together. If there's something wrong with a person's hearing, it often affects their balance. Hearing and balance are connected. If you guys didn't know, yeah. Hearing and balance, they're connected. Back to the picture here, all right? And so all those mapped out areas there. On the bus. All right, we're gonna skip a lot of stuff because this is gonna cover some of what we were just talking about. Primary somatosensory, I just mentioned that. Identification of the body region being stimulated. I use the forearm as an example. You can pick it. This is the sensory homunculi. So the blue represents parts of the senses. So your sense of the tongue, the thumb, the eye. Same thing, motor homunculi there. And it's all in the gray matter. Somatosensory association, determine size and texture, visual areas, visual association area, auditory area, olfactory area, gustatory area, taste, visceral sensory area, visceral organs, vestibular cortex, I'm sorry. All right, vestibular cortex, and that's just balance. The book defines balance as the conscious awareness of the head in space. All right, are you upside down or sideways? Back to the picture there. And then, all right. The brain, cerebral dominance, you guys. In the brain, most of us use one side of the brain more than we do the other. All right, that's called cerebral dominance. All right, it designates the hemisphere dominant for language. Left hemisphere, 90% of people. All right. The left hemisphere, generally, this is not always the case, but in general, controls language, math, and logic. So people who use more of their left brain, they're usually more gifted in language, math, and logic. Then the right hemisphere, insight, visual, spatial skills, intuition, and artistic skills, all right, in general. So when you hear, they used to talk about whether each person is right-brained or left-brained or things like that. This is what they're making a generalization about, okay? Now, you still use both halves of the brain and they communicate by these special little fibers that go back and forth that we really won't spend much time talking about. Myelinated fibers in their tracks. So let's pause. Myelinated fibers, unmyelinated fiber. What's the difference? What does a myelinated fiber have that an unmyelinated fiber does not have? Myelinated fiber has. What type of cell is wrapped around a myelinated fiber to make it myelinated? Gotta know that. That was like beginning of the chapter 11. In the central nervous system, it's called an oligodendrocyte. In the peripheral nervous system, good, it's called a Schwann cell. Okay. Myelinated fibers, unmyelinated fibers. What's another difference between them we just talked about today?
One's myelinated, it's faster than the other.
Good. Myelinated is faster than unmyelinated, right? And then the words I told you don't have to know that I'm not going to expose you, make you guys learn. Saltatory and continuous. Saltatory is myelinated fibers. Continuous is non-myelinated fibers. Because of the way the signal has to propagate itself. Anyway, we won't talk about any of those commissures, association, or projected fibers. I just wanted to like harass you guys about myelinated fibers, unmyelinated fibers, because you got to know. All right, this shows all these wonderful little fibers in the brain. It's not on the chest, but it's pretty cool. Fibers are shooting from all different parts. This is how, when something touches your thumb, you can make an association with something that's cold because you got association fibers that are running to other areas. It's saying, is that colder than what you touched the last time? Is that sweeter than the last thing that you take? There's all these fibers running all over the place. And of course, also here you see the white and gray matter. Just to point out, the edge is the darker part, that's the gray matter. All the middle of the brain is all white matter. Mostly white matter. Nuclei. Gotta be familiar with nuclei. Ganglia. I think we did, and I just want you to be familiar with the general definition of nuclei and ganglia, okay? Groups of cell bodies in the central nervous system are called nuclei. Groups of cell bodies in the peripheral nervous system are called ganglia. I'll say it again. Myelinated, that's white fibers, white matter. Gray matter. Gray matter in the central nervous system is called a nuclei. All right. Groups of cell bodies in the central nervous system are called nuclei. Those are decision making. So you have a nuclei for, we're talking about the movement of the thumb, nuclei for the movement of the knee. Those are nuclei, okay? Groups of cell bodies in the peripheral nervous system are called ganglia. Okay? Same definition, but different word based upon where it's found. Remember, 90% of the neurons are found in the central nervous system. So most of the cell bodies are nuclei in the central nervous system. There are a few in other regions of the body that are called ganglia. All this other stuff we skip. All right, and we'll skip even there. And the diencephalon, we'll talk about that in a minute. The thalamus, hypothalamus, and epithalamus, that's all part of the diencephalon. We'll see a picture in a minute. Here is the picture. All right, so the diencephalon, and I'm going to back up to the slide again. But the purple region here, the dark purple and light purple, all this is the diencephalon, okay? That's what we looked at as the thalamus in the sheep brain, okay? Diencephalon. If we back up, the diencephalon is made of three parts. There is the thalamus, the hypothalamus, and the epithalamus, okay? So thalamus, hypothalamus, epithalamus. I'm gonna come back to the picture. I just want you to see where it is. The purple egg shape here, that's the thalamus. The purple region here that I'm tracing, that's the hypothalamus. In the back here, this is the epithalamus. See, epithalamus. So this region back here, so all of this purple region here on top of the brainstem represents again the diencephalon. Okay. On the bus there, Now, I'm gonna give you a quick function for the diencephalon, specifically the thalamus, and what happens. When nervous signals are being sent to the brain or being sent from the brain, the thalamus functions like the post office for the nervous signal. It determines where the nervous signal goes. Because think about it. If we had a signal up here that was the tongue, and the nerve from the tongue is sending a signal, the nerve from the tongue, the signal has to go down to the spinal cord before it can get to, well, no, let's use thumb. Tongue's not good. Knee, let's use knee. So knee. Signal from the knee, it has to go down to the spinal cord before you move your knee, right? Because there's a nerve coming from your spinal cord to your knee to tell you what to do to your knee. But when it gets here, the thalamus, every signal has like a little zip code. And so the signal, it reads the zip code and sends the signal to the right nerve to go to the right region to make sure it gets to the knee. In a similar manner, if something is tickling your knee or touching your knee, that signal comes up through the brainstem to the thalamus, and the thalamus says you need to go over here because you're a knee signal. So it's kind of like it routes, it directs, it sends, it ships things to all its right places. That's one of the jobs of the thalamus. And the thalamus here again talks about that 80%. And what I was just talking about, the post office, the way the book describes it, it sorts, edits, and relays information. So it takes what's coming in and sends it to the right place. Hypothalamus has nuclei there. The hypothalamus has, these are nuclei. See these jelly beans? Those are in your hypothalamus. If you shake your head, you can hear them rattle. I'm just playing, but no. The jelly beans actually represent cell bodies or nuclei, groups of cell bodies in the nervous system. So you have a lot of different cell bodies in the nervous system in the hypothalamus that play a role in helping different things. You know, emotion plays a role there, blood pressure, pleasure is there, all right, in that region. And so again, you see hypothalamus, perception of pleasure, fear, rage, biological rhythms, and body temperature, all that stuff is there in the hypothalamus. Epithalamus, melatonin, right? Everybody loves melatonin, right? Right. So most dorsal portion, pineal gland is part of that, which also secretes melatonin, and that plays a role in controlling or regulating your sleep-wake cycles. All right, back to the picture there, and I think we're fit for a quick break. Yeah, 2 minutes over time. Guys, the things that I'm talking about are things you should go back and look at. Okay? Go back and read that section. So by being here in class, take a little note. Hey, he said this about this. He said this about that. Go back and read that and study that. Those are the areas of your test that I'm going to have in your test. Things that I know I did not talk about are areas I'm going to pull out of the test. Okay? So you guys, it's going to require you to do a little bit of reading, but I'm going to cover things a little more brief now so we can cover things faster. I'll say, hey, some things I might simply say, hey, this is important, you guys. Here's a quick explanation, go study that, and I'm going to keep moving, okay? All right. And then, if I'm able to do all that, what I will do on Monday after the lab final, we'll do a quick run-through, but we'll do a quick review for your post-test. But I got to get this done to give you that review then. All right. So 3 regions of the brain, you already know, guys. Midbrain, pons, medulla oblongata, you see it in the sheet. All right. These are parts of the brainstem. With the brainstem, there's 10 to 12 cranial nerves that we'll talk about later. This shows a picture of the brainstem. And here is the brainstem in the human. The purple is the thalamus that we were talking about. This green here, midbrain. That green, the lighter green that bulges out, that's the pons. This green here is the medulla, okay? The yellow structures sticking out are called cranial nerves, and we'll talk about those in the next chapter. Here again, same. Thalamus, midbrain, pons, medulla, all right? And then again, from a different angle, thalamus, midbrain, pons, and medulla, same structures, all right? You should be able to identify that. I don't think the picture's on your test, but knowing those structures, all right? The midbrain tells you what those do. We'll talk about that. And we'll talk about the nuclei in the midbrain. What are nuclei?
Central nervous.
Central nervous system.
Groups of the body,
Huh?
groups of cells in the central.
Groups of cells in the central nervous system that are
Gray matter.
gray matter, good, which is specifically called cell bodies. Good, you guys, you're getting it. All right. This shows the darker regions show cell bodies in the midbrain. Pons. All right. This shows the pons. Darker regions are cell bodies, and the medulla. And again, all the nuclei in the medulla. And in the medulla, you should kind of know this. In the medulla, your basic kind of, well, in fact, your whole brainstem covers your basic life functions, like your heart rate, your vasomotor center, controlling blood vessels, breathing, all right, you know, breathing, all of this is in like your brain stem, okay? Additional things that are in the medulla, specifically reflex actions, vomiting, hiccuping, swallowing, coughing, sneezing, those things you don't have to think about, or those things that a baby can do. All right. This shows a different region of the medulla. Darker regions, of course, are nuclei. The lighter regions, of course, are white matter. All right. The cerebellum, you guys know where that is, the little wrinkled structure on the back of the brain. All right. One of the jobs of the cerebellum is it sends signals for skeletal muscle contraction, all right, precise timing. Things like playing a guitar and playing a piano and very rhythmic things, all right. There's two hemisphere in there. There's arbor vitae, you know what those are, right? Tree-like pattern. This shows a picture of the arbor vitae. We won't talk about the peduncles. And you have the same like little homunculi in terms of moving the body in the cerebellum. And peduncles we won't talk about. All right. One of the things that the cerebellum does to give you an understanding, one of many things that it does, is it signals from proprioceptors and visual equilibrium pathways to continuously inform the cerebellum of the body's position and momentum. What does that mean? The cerebellum is constantly sending signals to best way to smoothly coordinate a muscle contraction. For instance, you guys, most of you guys I hope drive. If not, I'm still working on my senior in high school, pray for me. But making a left turn in traffic, you guys. If you're making a left turn in traffic and you got to turn into a road where a car is turning out and there's a lot of traffic coming, you got to time the car that's coming and make your turn, but you got to make that turn also in a way that you're turning and you don't hit the car that's coming and maybe you're driving a little too slow, a little too fast. You got to adjust the steering based upon the driving, right? We've all done that, all right? The thing which allows us to do that, part of it is the cerebellum. It's constantly making judgments based on, oh, the car's coming faster than I thought it was, I need to speed up. Well, as I speed up, I need to adjust my turn. This is what the cerebellum does, okay? One of the things that it does. And it also plays a role in non-motor functions such as word association and puzzle solving. All right, limbic and reticular system, skip it. EEGs, we want to talk about EEGs. All right, I'm going to skip straight to the EEGs here. There's 4 types of brain waves: alpha waves, beta waves, theta waves, and delta waves. All right, you want to be familiar with those. Alpha waves, regular, rhythmic, low idling. All right, in idling brain, you're daydreaming. Beta waves, less regular waves, you're mentally alert. All right. Theta waves, more irregular, common in children, uncommon in adults. Delta waves, deep sleep. So my hope is everybody has beta waves right now. You're engaged, you're active, you're paying attention. All right. Alpha waves are those that are daydreaming. All right. You're just sitting here trying to make it look like you're paying attention when you're really not. All right. Theta waves, these are children, you know, who can't pay attention. All right. ADHD, things like that, theta waves. Delta waves, and hopefully nobody has delta waves, deep sleep. All right. Here's a picture to show these waves. And the picture summarizes basically what I was just telling you. So alpha, beta, theta, and delta waves. Be able to know the different types of waves and what each represents, okay? And protection of the brain, all right? Around the brain, there's we talked about the dura mater in lab, but there's the bone, the skull, After the skull, there's 3 different meninges or 3 layers inside the skull. Then there's fluid, and then there's the blood-brain barrier. So all of these are layers that protect the brain from things like infection, things from physical damage, just protecting in different ways. The meninges cover and protect the central nervous system. And I'm gonna skip to the picture of the well, here's the 3 meninges that are possible, that are in the brain. You should know these. There's the dura mater, which is the most protective, the thickest, and the strongest. There's the arachnoid matter and the pia mater, all right? So dura mater, arachnoid matter, and pia mater are 3 layers that protect the brain. And in fact, we'll talk about it. You already know dura mater, that's that thick skin you saw. We have the same thing in our skull, all right, or in our covering our brain. The arachnoid matter is a thin, like arachnoid, like spider, arachnophobia, like web-like system that kind of sticks onto the brain. And the pia matter is a very, very fine layer of cells, almost like silt, all right? Really, really fine, like dust, okay? Is pia matter. So you got a layer of pia matter on top of the brain. Then you got a layer of arachnoid matter on top of that. Then you got the dura matter on top of that, holding everything in place, all right? And the picture, I think, for that is here. So here's your skin, your skull's here. This is the dura mater. There's 2 layers to that. See, this looks like little spider webs here? That's the arachnoid matter. And then on top of here, the gray matter, there's the pia matter. Okay. Can't see it, but it's microscopic. You just know those 3 layers. And then we just went over that. Dura mater is the strongest. All right, we will talk about all that. Arachnoid matter there. And then pia matter, very delicate connective tissue, clings tightly to the brain. And I won't ask you the detail of the pia matter, just know there's 3 layers that protect. Cerebrospinal fluid is the water. The brain floats in water. All right. So your brain is buoyant, it's floating in water. So there's not only cerebrospinal fluid inside the brain, there's cerebrospinal fluid around the brain. And it nourishes the brain and carries chemical signals. Here's a picture of the brain floating in cerebrospinal fluid. So you notice there's fluid all the way around the brain. But then, of course, there's ventricles in the brain also. All right. So there's fluid flowing around and in your brain. That's all I really want you to know. We're not going to worry about the 1, 2, and 3 there, or 4, the different. And we won't talk about choroid plexus either. That just forms the blood-brain barrier. You see it. 1 for ependymal cells there. Skip that. And we skip that. And the blood-brain barrier. Read the blood-brain barrier in your book, but I don't think there's but maybe 1 question on it. All right, spinal cord. All right. Spinal cord has bone meninges, like we said, the layers around there protecting it. We're going to talk about that. This is a picture of the spinal cord. And with the spinal cord, you should notice there's 31 nerves, or 31 pairs, of nerves from top to bottom. So there's 31 nerves that stick out on this side of the spinal cord, 31 nerves that stick out on this side of the spinal cord, and those nerves then go from the spinal cord all the way through the body. Because when something stimulates my toe, or my foot, it comes up the nerve to my spinal cord, which is my central nervous system, and that's where the decision is made. Or sometimes even to the brain, so I know what area of my foot is being stimulated, all right? So these 31 nerves that branch out from here go and radiate and reach and stretch through all of the body. And then here, that's where it tells you 31 pairs of nerves, all right? And that's all we'll talk about there. We won't talk about ventral dorsal commissioners, nope. A classic picture of the spinal cord, you should know this, because this pops up. I don't think it's on my tests, but maybe. This butterfly shape there, that's the gray matter of the spinal cord. A very unique, classic kind of picture, whatever you see. Spinal cord with gray matter, or tissue like this with gray matter in that butterfly shape, that's a region of the spinal cord. Again, spinal cord, you can see the layers around it, You see pia matter, arachnoid matter, neuromatter, so same as the brain. And you can see nerve pairs sticking out from there. Gray matter, we know what that is already. What is gray matter? I keep asking you guys that. What's white matter? Ooh, you need to know that. Alright. This just shows how the spinal cord plays a role in decisions. We talked about interneurons earlier. The interneurons are in this region right here. So incoming signal, outgoing signal, those 5 steps we mentioned. We already talked about gray matter, white matter, and I just threatened you guys to know that, hopefully.
Tissue in your brain.
What's that?
It's a tissue in your brain.
Groups of cell
Oh yeah,
bodies.
we got white matter in other places in your brain.
Groups of cell bodies in the peripheral nervous system.
White matter is not groups of cell bodies.
No, that's the nuclei.
White matter is myelinated axons. Gray matter is groups of cell bodies. Alright, we skip all that. Damage to the spinal cord. You can have a paresthesia, sensory loss, or paralysis, loss of motor function. Alright. Those are vocab terms. And we'll skip developmental aspects.
Wait, what was the?
Vocabulary terms. And then chapter 13, you guys are doing so good today. You've done 11, 12, and now 13. I'm proud of you guys. Questions? 13 is even shorter in time, all right? In 13, we're going to talk about the peripheral nervous system. Here's what I'm going to skip to, because you guys need to know. There's something called cranial nerves, all right? And nursing school said, shame on you guys if you guys are not exposed to cranial nerves, all right? So I want to expose you to cranial nerves and give you a trick to learn them, all right? And tell you how they'll be on the test, all right? So, here, everything outside the central nervous system, peripheral nervous system, we'll skip that. Sensory receptors, based on series. You know what? Ooh, you know what? I think I'm in the wrong chapter. Cranial nerve might be the next chapter. I'm coming back. Yeah. We're in our chapter. I do got to talk about this stuff too. I'm sorry. All right. So sensory receptors. All right. Sight, hearing, touch, taste, smell, all that stuff. There's different types of receptors. All right. They're based on the stimulus type, location, and complexity. Here's the thing, vocabulary words also to know. Mechanoreceptor, thermoreceptor, photoreceptor, chemoreceptor, and nociceptor. Let's talk about these real quick. All right. First, a mechanoreceptor, you guys. All right. Mechanoreceptors dealing with touch, pressure, vibration, stretch. So if something's touching you, that's a mechanoreceptor. Certain parts of your body, there are more mechanoreceptors than there are chemoreceptors. Sometimes there's more chemoreceptors than mechanoreceptors, all right? So mechanoreceptors touch, thermoreceptors sensitive changes in temperature. That should hopefully make sense. Photoreceptors, light energy. There's only really like one place you got photoreceptors. Where do you think that is? There you go. All right. Chemoreceptors, all right? Smell is a chemoreceptor. Taste is a chemoreceptor. There are also chemoreceptors in other places in your body. It's like pH changes. You know, chemoreceptors say, hey, pH is way off. Something's wrong. All right. Nociceptors. I want to sit down and talk about these for a bit. Those are receptors that are uniquely sensitive to pain-causing stimuli. Pain is one thing, all right, or something touching you is one thing. Pain from something touching you is something different. It's a different receptor, okay? Nociceptor again picks up with certain chemicals that detect pain, all right? Make this make sense, or give an example, a true example. There are certain very, very rare conditions where people are born with a condition called CIP, congenital insensitivity to pain. These are children, and when they're born, they can't feel pain. They can feel pressure. They can feel touch. They can feel tickles and all, but they can't feel pain. These are children where they realize early in life often the child will do something like grab a piece of glass and squeeze it to the point that they're bleeding, but they don't feel the pain. they'll touch a hot stove, and they feel that they're touching something, but they don't feel the burning. All right. Very, very rare condition where a person has mutations in these nociceptors, but it's a unique, a different receptor in our body called the nociceptor that I wanted to kind of mention, talk about, that plays a role in causing pain. So you should know those types of receptors there. All right. There's exterior receptors and interior receptors. What do you think those are?
Exterior's outside, interior's inside.
I just couldn't hear exterior.
Exterior's outside, interior's inside.
There you go. Upset stomach, interior receptor. Something crawling on your skin, exterior receptor. Pretty simple, right? And the rest of that, this just talks about the details of these receptors and what they do. I told you already, nociceptors are pain. You can go through this yourself, all right, and look at those. And this, I'm not gonna get into all the pictures, they won't be there. These talks about different types of mechanoreceptors. We're not gonna talk about the different types. And we'll skip that part. And the structure of a nerve in the peripheral nervous system. In the central nervous system, a nerve is just a cell. All right. In the peripheral nervous system, when we talk about a nerve looks like this. It's more than a cell, because this is a fascicle that has a bunch of axons in it. That's another fascicle, that's another fascicle, that's another fascicle. So this is a nerve in the peripheral nervous system, okay? Also, backing up, in the peripheral nervous system, endoneurium, perineurium, epineurium. Remember endomysium, epimysium, perimysium? It was on your test, right? In the nerve, same thing. Epineurium, around there, all right? Perineurium, around the fascicle. Around each individual is an endoneurium, okay? Same thing, it's just connective tissue, okay? Dividing nerves into functional groups. Now, because of this in the peripheral nervous system, you see how you have multiple axons, all right? And multiple, you got fascicles. In the peripheral nervous system, there are some nerves that are afferent and efferent, okay? Because you got all these axons in there. So you have the same nerve can send a signal to the brain, and the brain can send a signal back down that same nerve, or big, thick nerve, all right? It's usually not the exact same cell, but to wherever it goes in the body. That's a good picture. All right. Ganglia. What are ganglia? And what are nuclei? They're the same thing. What's the difference?
They're cell bodies. But
Yes.
Cell bodies.
Ganglia is in the
Yes.
peripheral nervous system.
Where's nuclei?
Central nervous.
I keep asking you guys that question. So now, cranial nerves, all right? This is what we gotta talk about, and then we're pretty much done with the chapter, okay? Isn't that fun? All right, cranial
Do we have
nerve.
do we have another chapter after this?
Me too. Shame on me, right? But, all right. But cranial nerves, you guys, all right? Most of them are mixed in function, meaning they're afferent and efferent, okay? Each nerve is identified by a number. There's cranial nerve number 1, cranial nerve number 2, cranial nerve number 3, all the way through 12. What you guys have to learn, and I'm sorry, I know you don't like it, but you gotta learn nerves 1 through 12 and the names of them, okay? We're gonna touch on it in just a minute, all right? So 1 through 12 and the names. I'm gonna skip ahead and come back here in just a minute. Bottom part I wanna talk about. Here's nerves 1 through 12 and their names. They're weird names. Nerve 1 is olfactory, number 2 is optic, 3 is oculomotor, all right? 4 is trochlear, 5 is trigeminal, 6 is abductions, facial, vestibular-cochlear, glossopharyngeal, vagus accessory, and hypoglossal. These are the names, okay? Here's how you can help remember them, okay? Backing up. At the bottom of this slide, there's a wonderful, weird sentence that you can memorize. On occasion, our trusty truck acts funny. Very good vehicle anyhow. Okay. If you remember that sentence, that helps you begin to put these cranial nerves in order, because we said on occasion our trusty truck acts funny, very good vehicle anyhow. Okay? You remember that sentence? You can begin to put all these nerves in order. If you compare cranial nerve number 1 with olfactory and cranial nerve number 8 with vestibulocochlear and so on, that is most of what you need to know on cranial nerves. Okay?
That we asked on the test, would you ask like, what is cranial nerve number 8?
Yes.
A, B, C, D?
Yes.
So they're like chronological. So they're like chronological, like 1, 2. You can
Could you,
interchange them.
you said, could you put them in chronological order?
Like you can interchange them. Like olfactory has to be number 1.
Yeah, olfactory has to be number 1. Yeah, olfactory has to be number 1. Optic has to be number 2. Oculomotor has to be number 3. Yeah, you can't flip them up like that. All right, you gotta memorize that. All right, that's one of those nursing school things. They're gonna expect you to know that. All right. Now, so learning that now. Let me back up to that sentence because that's a good sentence in my opinion. On occasion, our trusty truck acts funny, very good vehicle anyhow. Many of the cranial nerves have a disease associated with them, or homeostatic imbalance. Cranial nerve number 1, the loss of smell. So with COVID, the COVID virus was infecting the nose, even infecting the nerve cells. And while those nerve cells were inflamed, infected with replicating COVID virus, people lost their sense of smell.
Do we need to know each thing, like each?
Homeostatic imbalance, that's what I'm talking about.
So we need to know, like this one, loss of smell, or we need to know a disease that goes with it?
You need to know cranial nerve number 1. That cranial nerve number 1 is the olfactory nerve. A loss of smell
Okay.
is associated with cranial nerve number 1.
Okay.
All this stuff, the other stuff, forget that.
Okay.
Origin and course and
Right.
don't. Yeah. Cranial nerve number 2. All right. Results in anopsia, blindness. It's the optic nerve. Because remember we talked about optic chiasma in class? Here's the optic chiasma because it looks like an X. When you go this way from the optic chiasma to the eye, that's the optic nerve. It's just, it was cut off from the sheet. You didn't see a good nerve there. Optic chiasma, the X, coming away from the X, these are optic nerves. If there's damage to the optic nerve, guess what? There's blindness in that eye, okay? Ocular motor nerve, it moves the eye. So this one, you deal with, you can have eyelid ptosis, or you can end up with external strabismus where the eye rotates laterally. So the eye is just kind of, going laterally. You can't control the eye well. Cranial nerve number 4 also moves the eye. This one can often cause double vision. So one of the keys with this, cranial nerve number 4, trochlear nerve. If you see double vision, probably affects the trochlear nerve. Cranial nerve number 5, trigeminal. All right, this one, one of the things associated with this is tooth pain. All right, because this nerve here comes here, and you see how it radiates into the teeth, and it's considered one of the most excruciating pains known because this is a very, very thick nerve right here. So when this pain starts to radiate and hit that thick part of the nerve, tooth pain is considered. Some people say it's something else, but they say it's the worst pain ever. Abductions, again, is also moving the eye, cranial nerve number 6. At rest, the eyeball will rotate medially, so when the eyes rotate inward, that's cranial nerve number 6. All right. Outward, 3, inward, 6. The facial nerve here, with the facial nerve is something called Bell's palsy. Bell's palsy. Somewhere here. Key with the facial nerve, what I'll harp on, Bell's palsy. If you see Bell's palsy, think cranial nerve number 7. And so I'm pointing out what to know, you guys. You can skip the rest of the stuff if you're highlighting. Taking notes. Visiting the cochlear nerve, hearing imbalance. All right. So damage to your cochlea, hearing, or damage to the semicircular canals, balance. They all travel through the same vestibular cochlear nerve. All right. Glossopharyngeal. From glossial, all right, tongue, pharyngeal, pharynx, all right. Injury to the glossopharyngeal nerve impairs swallowing and taste. The vagus nerve, this is the longest, not the thickest, but the longest nerve of the body, all right. And you see this nerve comes from the brainstem, goes to the heart, the lungs, the spleen, the kidney, the intestines, the stomach, liver, gallbladder, all over the place, all right? And so something dealing with your visceral organs, digestive system, heart, something like that, is often related to cranial nerve number 10, the vagus nerve. And then cranial nerve number 11, the accessory nerve. All right. This here, shrugging of the, sternocleidomastoid muscle paralysis, shrugging of the shoulder, and the trapezius muscle becomes difficult. So, you know, sometimes you sleep wrong, you know, you wake up with kind of a pinch or something like that. That can be an issue with the accessory nerve. And lastly, hypoglossal nerve, under the tongue, under glossal tongue. This nerve, all right, damage to this nerve will cause, or damage to the hypoglossal nerve cause difficulties of speech and swallowing. If both nerves are impaired, the person cannot protrude their tongue. If only one side is affected, the tongue deviates toward the affected side. So tongue will move toward the side that's affected, all right? And so tongue leans one side or the other, hypoglossal nerve. All right, we're pretty much done with the chapter 13. Questions? No questions? All right. You see, I've done this before. You guys don't like it, but I've done this before. All right. Plexus, we're not gonna talk about any of this stuff. And back to, I mentioned this reflex arc again. It just pops up in every chapter, just to make you think about it. Receptor, something pricks the skin. There's a sensory neuron, which is afferent. It goes to the interneuron in the gray matter, which is the central nervous system. From the gray matter of the central nervous system, it sends down a motor neuron to the muscle to tell you to move your hand. Yes?
Do we have a written portion on our test?
No.
Sweet. Okay.
No written portions. All right, chapter 14. All right, everybody good, chapter 14?
Mm-hmm.
All right, autonomic nervous system, and if I get to 14, we're good. We can do the rest, well, not the rest, but the post-test on Monday. All right, autonomic nervous system, you guys. Autonomic nervous system, remember, autonomic nervous system is stuff that happens automatically. Automatic and autonomic are not a good, they don't really mean that, but if you can remember things that happen automatically, like glands, sweating, you know, those are autonomic stuff, okay? Heart rate, beating. Now, we'll skip all of this. In fact, there's very little of this that I cover. Preganglionic, postganglionic. Sympathetic, parasympathetic, I do want you to know that, all right? Anybody know the difference between sympathetic, parasympathetic already? One is fight or flight, the other is resting and digesting. Which is which?
First one is
Parasympathetic is resting and digesting. Sympathetic is fight or flight. All right. So, parasympathetic division, all right, of the nervous system promotes rest, maintenance activities, conserves energy. Reading a book, relaxing after a meal is parasympathetic. Blood pressure, heart rate, respiratory rates are low. GI tract activity is high. Sympathetic is fight or flight. You should know the difference between sympathetic and parasympathetic. All right, blood flow is shut at the skeletal muscles, bronchioles dilate, livers release excess glucose. All right, You're ready to fight or run. When you break down sympathetic and parasympathetic here, all right, we won't even talk about that one. That's talking about pre and post gate failure. And we already talked about reflex arcs. 1, 2, 3, 4, 5. All right, same thing there. But the visceral reflex arcs going to the internal body, they travel sometimes along unique pathways. And because they travel along unique pathways, there's something called referred pain. It's not on your test, but it's cool to know. Here's referred pain. Referred pain is here. So when someone has liver pain, it could be here where the liver is, but sometimes it's here also in the neck because of where the nerves are running. When someone has, for instance, heart pain, because of where the nerves are running. Or gallbladder pain is pretty cool, in the shoulder, because of where the nerves are running. And so sometimes when you guys get into your careers, if it's nursing or medicine or whatever, and someone goes up with a pain in a certain region of the body, and you're like, oh, let's run this test on it. Oh, doc, that is my shoulder, doc. You're like, no, but we're gonna run this test. Oh, but you know, it's my knee. Yeah, I understand. We're gonna, because of referred pain. They know that often pain in one part of the body can often indicate a deeper issue internal to the body.